Okay, so hi, I'm going to be talking about dice. Which is interesting. I played, I'm Spencer Catallani. Playing D&D, and I always get distracted with the dice because they're like, oh, yeah. So like the basic die that everybody knows is a cube. And if you look at like the standard, opposite sides add up to 7. And that's like, oh, how many flips are there on a die? 21, 3 pairs of 7. You know that, you know something immediately about it because you know this. So what's, there's like another property on the common 6, like a cube die that people don't usually notice. And it's, all the evens are about a corner. So if you rotate, you can go from 2 to all the evens. And also there's a like this bottom face would be 3. So you see that 3 and 6 are next to each other, and you can flip them. You can go from 3 to 6. So it's like, oh, do you guys know like groups? Should I explain groups? I'll explain groups. Yeah. So there's like symmetries of the cube, and you can invert them, and they compose associatively. You know? So it's just everything behaves nicely. And if you look at, like, say we take three symmetries, like, oh, rotate here, flip, something like that, and you take all possible compositions. You could call that the subgroup generated by those. So is there some subgroup such that it takes a number to all multiples of that number and only those? So that's what I find interesting on dice. There's other things. Like if you look at some octahedral dice, the sum of the numbers about a vertex is constant. Right? And it's the only platonic solid where that can happen, because it's the only one with 4 faces incident to a vertex. You need an even number. But that's beside the point. So if you look, every number some dice we want it to be a convex polyhedron, you know? So just a basic shape, what you think of as a shape of possible dice. Well, 1 is on it, so we want some subgroup such that it takes 1 to every face. So in particular, there should be some symmetry that takes a face to any other face. So that's being called face transitive. That's the regular polyhedra, like icahedron, cubes, tetrahedra, the platonic solids. They have this property, and they're edge transitive. So there's a symmetry taking an edge to any other edge, and they're vertex transitive, which I think you can guess what it means by now. It takes vertices to vertices, all of them. So this is saying that the only polyhedra we want to consider are those that are face transitive. So what are those? So we have, like I said, the 5 platonics. And it's like that. I won't draw all of them, just enough to guide into it. So that's and in particular, look at these two. So if you take every face here and put a point on it, and then for every vertex, you put a face. So just replace faces with vertices and vertices with edges. It's called dualizing it. And if you do that with an octahedron, you take its 8 faces and you replace them with 8 corners. And then you take its 6 corners and you replace them with 6 faces. So these are dual. And the tetrahedron is still dual. So that's just, so then we have 13, they're called Catallani solids. And they're kind of, they're like hard to visualize. They're like, the faces aren't regular polyhedra.
Is this 10-sided one of them?
That is one of them, yeah. The D10 is a Catallani solid. So a good way to think of them is the Archimedean solids are defined as being vertex transitive. So just take their duals. So these are the duals to the Archimedean solids, which are like easier to think of. And these include, like, you know, like a soccer ball, hexagons, pentagons stitched together. That's a truncated icosahedron. That's Archimedean. If you take a cube and you cut all the corners, that's a truncated cube. That's an Archimedean solid. And just like basic things that you can do to platonic solids will give you Archimedean solids. And then there's 2 infinite families. The bipyramids, you've already seen one. It's the octahedron. You take 2 square pyramids of them. But in general, you take some shape. Put a point here and a point here. See, you can rotate and flip, and it's face transitive. And then you have the D10, where it's like this, but the middle line's squiggly. No, that's terrible. Something like this. So then you're like, okay, well, we have 18 and 2 infinities that we can choose from. So which of these are good? Can have a numbering such that this property holds? Yeah?
You said 18, but aren't platonic solids also Catallani solids because they're phase transitive?
Yeah, but the 13 Catallani solids are the non-platonic.
Oh, okay.
Yeah. Yeah, and technically these should also be Catallani solids. It's just like a cultural thing why we separate these as different families. So this seems like a difficult question because, like, combinatorially, this is disgusting. Some of these have like 120 faces. I'm not going to try, 120 factorial combinations of faces and see if, there's one that has this property. And then we have these 2 infinite families, so that wouldn't work anyway. So what's the way to do this?
Could you repeat the property of them?
Sure. That we're like trying to enumerate? Yeah. So, so number, so like assign numbers to faces. It's good if for any number m, there exists a subgroup of the symmetry group of the shape. such that the orbit, that's the elements accessible by application of an element from here. So if you look at this, the orbit of one of these top faces under a rotation is the top. You can get to every face at the top, but you can't get to the bottom. So the orbit of this is the top. If there is a subgroup such that the orbit of the face on the subgroup is all multiples of that number.
And then you said the cube was such an example of this?
Yes. Do you see the evens are here on the top. So you can just do this rotation. And then this is 3 and this is 6. So this. Do you see? Those are both cyclic subgroups, so that's like nice. Yeah?
So 2 questions. Are we doing multiples modulo n?
No, that's later.
Okay, and second question, are we asking whether or not there exists a numbering or whether it applies for all numberings?
Take a numbering.
Okay.
And then for all, because, yeah, it doesn't really matter in the way I've done it because I don't fully answer the question, but it's just like.
So the problem is like, given a shape, does there exist a numbering such that for every number there exists a subgroup of the shape such that the orbit of that number under the subgroup is all the multiples of that number?
So this is stated explicitly in terms of symmetries, right? So you might want to look at the symmetry group, right? So a good example is the D10. Let's look at the D10. It's this is what it looks like on top, and then you have the outside. So let's look at 3. There's 3 multiples, 3, 6, 9, no more. So we want some subgroup of order 3 in the symmetry group. So if you look at the symmetry group, it's 5 rotations, and then just flips. So 3 doesn't divide the order of the symmetry group. So by Lagrange's theorem, which is a group theory statement, just that the size of a subgroup has to divide the size of the group it's contained in, there is no subgroup of order 3 in here, so you can't put a nice numbering in a D10. You see, so I tabulated some results when I was interested in this. So, for example, it's called a Distiakis dodecahedron. You know this?
Yeah,
How do you know this?
I'll tell you later.
It has 48 faces and its symmetry group. This has 48. You see there's 48 symmetries total?
Did you say it was a dodecahedron of some sort?
It's a Distiakis. It's a lot of these prefixes mean you do something to it.
Oh, okay.
Like a truncated icosahedron has like 32 faces. It's something like, we start with that. So it has 48 faces and 48 symmetries. So an interesting thing to notice here is there's 48, there's the same number. And for every face, for every pair of faces, there's a symmetry that takes one from the other. But they're the same number, so there's just enough to do that. So fix a face. Say this is home, fix a face. Then its symmetries are in one-to-one correspondence with the face. So like look in cube. Nah, cube doesn't have this property. But this is called being a homogeneous space. It's just, you can think of this shape as the group, just if you forgot it had an identity element. So just as like a detour, this is like an important idea. Just talking about geometry, like Euclidean geometry, there is no base point. You don't talk about vectors, you just talk about points and lines. And you can talk about the length of a line between 2 points. So you can subtract points and say like, oh, here's how you have to translate to get from one to the other. So that's what you're working in, this affine space, is a principal space or a homogeneous space for the real numbers of that dimension. And that's what a coordinate system is. You're associating this principal space with the group. And with this new group structure, it's more than that. It's a vector space. With this vector space structure, you can do geometry super easily. That's what Descartes did. That's, in differential geometry, you try to generalize this and you work in coordinates. Locally, it's a homogeneous space, but you can't look at it globally. That's where all this nice structure comes from. It's locally a vector space. It's locally an affine space, stuff like that. So this is it's like a baby example. It's a polyhedron. You can understand it. But this does not permit an interesting number, because if you look at the multiples of 5, there are 9. And 9 doesn't divide 48. So this doesn't. So you can go through and around half of these 18 can be ruled out in this way. The others have way too many faces, and they actually probably permit a numbering. But what's the point of writing it out, So you can ask yourself instead, I don't actually want numberings. I just want to say how many about there are. So that's useless if there are still 2 infinite families. Because it's like, 18 and then some infinite number. That doesn't make sense. There's an infinite number. So you want to talk about, are there infinitely many of these such that this holds? And I haven't proven this. I feel like this is a good exercise if you liked. We can talk about it later if you are interested in this. I wrote a computer program that tested for cases up to 10,000, and only the first 12 accepted something. So this is very likely that there are not infinite families. And it's one of those things where you just need one number to be off, so you expect it to hold for large enough numbers. But I don't know yet, so it's an exercise, But yeah, so with this, we see it's very restrictive. You just need one number to throw off the numbering. What if instead, these are finite, just finitely many faces. Why are we using this k belonging to n? Why don't we do why don't we do a modulo the number of faces? Because that's what we were doing with the cube. With the opposite sides add to 7. You say that opposite sides are inverses mod 7, additive inverses. A lot of these statements you can make about numberings of faces are more natural if you talk about it modulo the number of faces. So then, these problems, you just need one number to throw it off. It just needs to be co-prime, something like that. Disappear. Because if something is co-prime, so say like the D10, we couldn't do it because 3. But 3 is co-prime to 10. So if you look at all the multiples of 3 modulo 10, it's everything. So you've already included that in phase transitivity. So the problem becomes one instead of divisible but not well, you know, and then actually numbering the faces. But this was the part I really liked. This was like what made it worth it for me. We know of at least one infinite class of families, or one infinite family, where this condition holds. So there are infinitely many interesting dice under this definition, but likely not under this. So what's the what are the dice, this family? It uses this idea of the homogeneous space. So think of, if there is going to be an infinite family, it has to be one of these infinite families. So start off with a bipyramid. And co-prime numbers you don't have to care about. And bipyramid split in half, it's a bipyramid. So what if we could put all the co-prime numbers on the bottom? That would be nice. So to do that, you need that it has 2 to the n faces. We start with, I'll do an octagon.
Wait, what do you mean 2 to n faces? If n is the number of faces.
Oh, I just mean like a power of 2. So you see it's like this one on the top and on the bottom. So then you can put all the odds on the bottom. They're co-prime, so the full symmetry group is what you need. You know, they're just like 1, it doesn't matter. So you only need to care about the evens, so you put them on top. And the number of symmetries at the top is the same as the number of faces. It's like that 48 case over here. This is a homogeneous space for Z in this case, that would be 8. So just choose home. This is 0. And then
Wait, I thought we were numbering starting from 1.
no, it's odd, so we put that on the bottom.
Okay, so
Oh wait, sorry. This would be 8,
okay,
but like 8's the identity.
right,
Yeah.
okay.
So then we put 2, and we see that we can associate this face with this symmetry. So all the multiples of this face are all the multiples of this symmetry. Oh yeah. So then, what are the multiples of 4? Well, we associate 4 with this symmetry. So multiples of 4 are this. Yeah, and then you can just do this for every one. For every face, you associate the symmetry that you need. So there's this infinite class. 2 to the n, you just put the numbers z mod 2 to the n on top. And this makes it clear why we call it clock arithmetic sometimes, these modular numbers. This is a clock. It is going counterclockwise, so like, if you did it the other way, it'd be a clock. So a clock is also a principal homogeneous space. But yeah. Okay, so if you take this, as you increase the number of sides, it kind of looks like a circle, and these symmetries get smaller and smaller. If you tend to some limit, you get a circle, and that's what a clock is actually. It's the circle group, and we call it that because the circle is the principal homogeneous space for the circle group. You know I'm right.
Isn't the clock like Z60 though?
No, because time's continuous.
How do you know?
I know. That's what I thought. That's the thing. Aristotle didn't believe in atoms, and people are like, "Oh, he was so stupid." How do you know atoms exist? Okay. So that's like, geometry and algebra. It's just like you think of it and you're like, "Oh, algebraic geometry. It's this big scary subject." It's like algebra's made for these toy examples, and like basic stuff. So then this is like a way to like think about algebra. Any questions?
Okay, so for this D10 or D20, wait, this has 20 faces, right?
This
Or
has
16 faces.
32. Because it's 16 on top, 16 on bottom.
No, it has 16 faces. It has 8 on top.
No, it's oh yeah. Yeah, you're right. Yeah.
And then the multiples of 4 are 4, 8, 12, and 16, which is 0.
Mhm.
The multiples of 6 is 0, 6, 12, 18.
Wait, it's you go through 4 every time. So it's 6, 12, 2,
Yeah.
8, 14, 4, 10. It's all.
Okay. Yeah. Right.
And this didn't rely on it being a bipyramid. You can also do this on this shape. And a nice thing is these have a map. Just choose a symmetry you want that goes from the top to the bottom. And say that a number here goes to its inverse mod n plus 1. Then you have the basic symmetry that like motivated this on this shape too. But you can't have the octahedron one where sides about faces about a vertex sum to the same number. First of all, because there's so many more up here than down here, but you can't even have that for like this vertex. You can't have the sum about here, the same as sum about here, because we've already said what the numbers are. There's no natural way to extend that here. I think I said, oh. I think I've said what I want to say unless there's any questions. I know I didn't speak for long.
Any questions?
What about the non-infinite families? Do we have any nice things there when we do modular arithmetic?
See, here's the thing. Modular arithmetic gets rid of barriers to there being interesting dice, and I was really only interested in the barriers. So I like, there'd be more cases that you have to check here for this. I don't really care about finding the actual interesting dice. I just want to like put some kind of balance on what dice can be interesting. Anything?
So what is the conclusion? Sorry, like, what's the
What's the meat?
Yeah. So
I like the big thing for me was there's finitely many of these dice, but infinitely many of these. that's like, this is such a small change. But this is more natural. Naturality.
Right.
Alright.
Nice.